In this video, we're going to introduce trees for regression, or what I often refer to as correlation models. Here we have a tree, and the idea with tree methods is that you still have your predictor, covariate, independent variable, whatever you like to call it, up here. And the idea is that we're going to split up the values of our predictor variable into multiple branches until we end up with these states down here that are referred to as terminal or leaf nodes. So each of these boxes is a node. And in the first box, we ask the question, is the temperature greater than 30 Celsius, of course. If that is true, then the trees die because it's too hot. If the temperature is less than or equal to 30, we end up over here. And then we ask the question, is the temperature less than 0? In that case, that's true, the tree also dies. If that's false, then the tree lives. So what you can see is this allows us to take and break up a value from a covariate and make these splits. These are referred to as branches, where we split up the value, okay? And then we end up with these different states. And so with this, we can model very complex phenomenon and discretely. So it's not continuous anymore. And we end up down here with these leaf nodes. And the boxes are called nodes, and the lines are called branches. You may notice that it's upside down from what you might think a tree would look like. You do sometimes hear this being the root node, not very often. We just talk about nodes and branches, and off we go. All right, so there's a number of different types. Classification trees, the predicted outcome is a class. This would be something like cover type. More commonly, we talk about that as categorical, but it is talked about as a class within classification trees. So cover type, vigor, species are all things that could be a model with a classification tree. And this is really where trees come in my opinion, because it's the only method we have that has a categorical variable for the response. So that's pretty cool. Regression trees are one where it's a value, and you'll hear talked about as a value. It's really continuous value. People use it for this, use trees for this. I think we have other methods that usually do better. Boosted regression trees are one of those, and this combines these together, often with a large number of branches and nodes. And random forest is sort of the extreme of that, which combines many trees together to improve the fit. And you can have thousands of nodes and branches in a random forest, and then you can fit it to continuous data. But of course, then we're also probably overfitting the data. Okay, so here's a classification tree. You might have reflectance within the remote sensing world, a raster that has reflectance in it, and you could take each pixel and say, well, if it's less than 0.1, then it's going to be water. Otherwise, if it's greater than 9, that's going to be snow or cloud. It's very light colored. Or in between is going to be some type of ground or veg cover. So a very simple tree for classification. You can see then you end up with water, snow or cloud or ground. So very powerful for modeling categorical response. When we look at this as a response, which we don't usually do, it looks kind of strange, right? Here's our independent variable, our covariate, and as it changes, we have these different categories. So it doesn't really fit with doing response curves for classification trees, and you don't need to do them. Regression trees, on the other hand, here we have precipitation, different levels of precipitation, giving us different levels of suitability. So again, we're sort of modeling a continuous variable here. If you get enough nodes, you can start to see this being continuous. In some cases, it does make sense to have continuous values modeled as categorical, but not too often. If we look at this one as a response curve, you end up with, again, your covariate down here, and then you end up with these levels for the output. So you will see regression trees these types of plots, our traditional response plots. You will see these for regression trees, particularly when they have lots of nodes, because it's simply difficult to visualize the tree itself. Okay, so classification of regression trees. This is where we're headed. This is why it's called CART. So classification regression trees. Predictors can be continuous or categorical because it will simply pick the right one. They're pretty easy to interpret and understand as long as they're not too complex. They are robust. They're pretty easy to validate. Statistical methods are well understood. However, they can still make really complex trees that overfit the data. This one is still not too complex. It's just an example to show you that they're used in GIS. Okay, in this case, different geospatial variables are used. Here's one for California housing prices that I don't really understand because they use latitude and longitude. And here's a map of that. So they're cutting up California's latitude and longitude, which is interesting. But yeah, I don't know why they did this. Anyway, so I'm not sure why they are used sometimes when we could use other things. Now, in this case, they may not have had the data, so this is all they had. When we move into using trees with R, there's two libraries that you'll see out there. One is called Tree. The other one is called rpart. Rpart is newer and it's used by Plant if you're following along in the Richard Plant's book. The way that the trees are calculated is internally there's a cost complexity measure. And don't get too confused on a CP parameter. I'll come back to this. And you can see here that what we've got is we've got the relative error, the amount of error, okay, and then we have plus effectively the complexity. So when trees are created in R, they're trying to minimize this value, so trying to minimize the error and minimize the number of the complexity or the number of nodes inside of your tree. So this is very similar to AIC, same type of approach where we're trying to get a good fit to the model, but also limiting the complexity. The relative error, this is not R squared. You will see R squared scattered around, but this isn't a linear regression, so the R squared is different from what you've seen in linear regression. It's called relative error. It's just the sum of squares, so it's effectively the residuals, how big the residuals are. However, they use 1 minus this value. So we'll talk more about that when we actually show how to use this in R. And then there's the complexity piece with the number of nodes and a complexity parameter. This is one of the things that you can change is if you increase this value, that will simplify your tree because it's going to punish more for having lots of nodes. Okay? And otherwise, if you bring this value down, it's going to go ahead and have less impact and you'll end up with higher complexity. Okay? And we'll show you that. All right, also there's a way to control it. So we'll do a traditional model in R in the next video, but there's also this other object you can create to control it because there's a number of different parameters, a little bit more complicated. And these are the parameters that we can use to control the fit, the minimum number of data points in a node before a node is split. In other words, if you're down to having just a few entries, a few number of data points represented by one node, like 4 or 5, you probably don't want to split based on that. So you can change that. More commonly, you'll use this complexity parameter, which as you make it smaller, you get more complex trees. You make it larger, you'll get simpler trees. And this is also a good time to read the documentation in R. It's painful, but important. So here I just searched for rpart. And it's kind of nice that R has the name R. A lot of times you'll come to the crayons. Okay, this is the traditional documentation for R. Okay, and here you'll see rpart.pdf. So this is the traditional documentation. It's done in a PDF. I think it's a little bit hard to access compared to a lot of documentation. You will get more familiar with it over time. However, more and more I'm coming up with this link, which these look better. Anyway, so here's rpart, and here's how to do an rpart model. And you can see it's got our formula, same formula we've done before for other correlation regression models. And then you've got your data, and then a bunch of other stuff. The only other one I'm going to really focus on is control, because if you note down here, you'll see control has rpart control. So we need to go to another piece of our documentation on that. I also do want to show you that, notice it's got this ... that says rpart may also be specified in rpart. Oh, that's kind of handy to know. And then there's examples which tend to be of a lot of value the first time you try running one of these modeling methods. So if we go here, in here you'll see, R part control. There's the number of minimum splits. There's the CP parameter. There are other parameters, but those are the only two that I'm going to play with. So I'll do another video. Oh, wait, one more thing. So there are some additional resources out there, not as much as for some of the other methods. And then you're into the R documentation. Have fun.